let's get started. We are going to be doing one more question from the channel. And I am now going to murder some electricity formulas. So I apologize beforehand. You can have a good laugh at me later. This I do know, right? It's a very, very basic formula, isn't it? The voltage is the current multiplied by the resistance, right? V equals IR. What we're looking at here, Bailey, stop being a pain. The two of them are trying to share the same bed, but he's not good at sharing. So I believe that number is 460, I'll assume it is. We are looking at a system here where the current and the resistance and the voltage are changing through time. And at one instant in time, the resistance is 460 ohms. The current that's passing through the circuit is 0.07 amps. The rate at which the voltage is changing is it's going down by negative 0.02 volts per second. And the resistance is changing by 0.01 ohms per second. And we are now trying to estimate, based on this information, what is the rate of change of the current? So how's the current changing? That'll be in amps per second. So voltage, current, resistance, they are not fixed. They are now considered as functions of time. So if I take this and I differentiate it with respect to t, I get this. If I take these two guys, essentially, aren't I looking at a product rule? So it's like a chain rule question where V, I, and R are the variables, right? These two are the variables, and that's like the Z, and all of them are in terms of t. So F dashed is that guy. Times G, which is that guy, plus F, which is that guy, times G dashed with respect to t is that guy. Are we okay with this basically as our formula for the chain rule? Although I haven't maybe written it the way you see it, but isn't that essentially a product rule thing? Right. Now, I know this guy because they told me it's negative 0.02. I don't know that guy, but I'm going to find out what it is, so I'll write that down. The resistance was 460. The current was 0.07. And this guy was 0.01. So I'll do a little bit of tidying up here. And if I multiply these two together, I better do it with my calculator or I'll end up with 102 here and 0.0007. Okay. I'm not going to finish this question. The hard part's done. Would you agree that all I need to do now is solve an equation to find that guy and we're finished? Yeah. So you could take any equation that you have in electronics, electricity, chemistry, but when you do those equations, aren't they typically fixed? In other words, nothing changes through time, right? Can you see that you can now adapt it, provided you're told some more information? Not just told these two, because you obviously need them, but you could also be told these two as well. And if you tell me enough information, wouldn't I be able to find the rate of change, how something is changing at that snapshot in time? That's pretty, I think that's pretty cool. And we are finished as far as what we need to do for this week's homework. So I'm going to start and do some more. And although this is not due this Sunday, I suggest that you do them anyway. You've got a week on Sunday for this stuff. We're going to look at what's called directional derivatives. And what's called the gradient vector. So that's what I'm going to kind of deal with today. Okay. Make a really bad attempt at drawing a surface in 3D. Can you imagine we've got a hill and it looks something like this? And I'll try and put in some like contour lines like that, right? Now, if I just take this part of the hill and there's the rest of the axis going this way and this way. Can you imagine a point, let's do it in green, here. Maybe that point is 1,2. If that point goes up, would you agree that it touches the surface eventually? So that green dot would be the point on the hill that's directly below 1,2 on the XY axis. So far, so good. Right. Now, on that surface, when we get the derivatives, so let's call that surface z equals f of xy, right? When we do our partial derivatives, dz by dx, and the other one that we do is dz by dy, they're just special cases of slopes of tangent lines. One, you cut the shape in the x-axis direction, and the other, you cut the shape in the y-axis direction. And if you did that, don't you get a little curve, and it's this point here, and that dotted line ends up being, you know, one of these two? Well, what is a directional derivative is that you don't, excuse me, you take this point, but you don't go and look at it, what's the slope if you cut it that way, or what's the slope if you cut it that way? What you do instead is you imagine what the slope might be if you went in that direction. So analogy, can you imagine you're on a hill and you could travel north, you could travel south, but couldn't you also travel northeast? And in some parts of the hill, won't you be climbing quite steep? In other parts of the hill, won't you be basically just flatlining? You'll be just going around the hill. And in others, can you imagine it's not so steep? And then obviously, if you point the other way, aren't you going downhill, in which case it would be kind of negative slopes? Wouldn't it be helpful to be able to tell what the slope of the hill would be on that surface in any given direction, right? And that's what a directional derivative does. These are just special cases of directional derivatives. This one is the x-axis, this one's the y-axis, right? That's all they are. What we're going to do is expand that to be any direction at all. Before we can even deal with how do you calculate that, because it's going to be a number, it's going to be 4 or negative 42, we need to find a guy called the gradient vector of a function. So imagine I have a surface, a function, z equals f of xy. The gradient vector is typically written like that. It's an upside down triangle, and you just say grad f. That's typically what people say out loud. And that's what we call that's the notation for a gradient vector. And the little arrow above it is the convention that you use when you mean something's a vector, right? Now, when you look at it in textbooks, don't they do that? They make it bold. You know, all vectors are bold, right? So just in case you look at the book and say, what happened to the arrow? They don't need it when it's a textbook. We kind of have to in the human world. So let's tell you how you calculate it. So to get this thing called the directional derivative, I need to know how to get a gradient. And it's a vector. And that's how you do it. You see, you find the partial derivative with respect to x, comma, the partial derivative with respect to y. So let's do one. Suppose I have a surface, x squared plus y squared x cubed. And I wanted to find the gradient of that function. Then I differentiate this with respect to x, comma. I differentiate this with respect to y, comma. And when you differentiate this function with respect to x, you get 2x plus 3y squared x squared. And when you differentiate this function with respect to y, you get 2y x cubed. Are you comfortable about how you find a gradient vector? Would you agree it's just two partial derivatives, one for an x, one for a y? No biggie, right? As long as you know how to do partial derivatives, you can always get a gradient. How about a function like this one? Couldn't you get, by the way, that's a two-dimensional gradient vector, right? It's got two parts. Couldn't you extend the gradient idea to a three-dimensional function, right? Or a fourth dimensional or a 20th dimension? In this case, the gradient function, I don't need to put x, y, z, I guess I'll have to now. That's kind of redundant. Differentiate with x, differentiate with y, differentiate with z. Doesn't that mean now that we can do gradient functions for 20-dimensional space? So if some theoretical physicist says, you know, when you do black holes, you need to work with 20 dimensions, we're going to say, no problem, we can do it. Right? I want a gradient in 20 dimensions. Okay, I'll probably run out of letters of the alphabet, so they typically just call it x1, x2, x19, and x20, right? They just put subscripts on the variable to represent each one of the 20 dimensions. So far, so good? Right. Now, again, I haven't done anything yet to tell you how to calculate them. This is the start. I seem to have lost my window. Are you here, guys?
I'm still seeing your paper.
Okay, let me. Okay. My window went weird. I get kind of worried when I'm on technology and things disappear when I don't expect them to. So next one is really just for completeness sake. And you should say, you don't need to tell me that, I knew it, but I'm going to tell you anyway. You're going to have to find unit vectors to do this process. So if I give you a vector v, and it's 1, 2, 3, because I have no imagination, isn't a unit vector a vector in the same direction as v, but whose length is 1? And we typically call the unit vector u, and its formula is 1 over the magnitude of v, and v. So the magnitude of this vector is the square root of 1 squared, 2 squared, add 3 squared, which I believe is the square root of 14. So the unit vector will be 1 over the square root of 14 of the original v vector. What are you barking at? She doesn't want your toy, you little... Just... He's being a pain right now. So put that package together. Strictly speaking, I should probably tidy that up, but I'm not going to bother. You can do all the style points at the end, right, when you've finally got a number, because at the end, you're going to get 42 or 5 root 3 or something, right? And then you can deal with the tidying up. I'm not going to bother tidying that up right now by rationalizing the denominator, because we don't need to. Are we comfortable? You remember how to do unit vectors, because you're going to have to do them in these questions. Call that done then. So, quick recap. You know how you get a gradient vector. You know how to get a unit vector. Can't you get a unit vector in a 20-dimensional vector if you wanted? I mean, there's no limit to how many, right? 2, 3, 23. Now, a different kind of situation for a unit vector. So I'm going to try and show you, because this is only going to be in 2 dimensions. I want you to imagine that I've got a vector, which I'm going to call v, right? Going in that direction. And I'm not going to tell you its components. Right? I'm not going to tell you it's 3, 2 or 1, minus 9 or whatever it is. I am just going to tell you that the angle that it makes with the positive x-axis is theta. Then you should be able to tell me what the x and y components of this vector are. So if I tell you that the radius or the distance, we'll call it r, right? Can you remember r cos theta being the x and r sine theta being the y? Can you remember that? Now, if I do the same thing with one little difference, I make sure that the distance, right, of that vector is 1. Don't I now get a unit vector? Because 1 times cosine theta is cosine theta, and 1 times sine theta is sine theta. Are we okay with how you can get a unit vector who's traveling in a direction theta with a positive x-axis? So I've got all the pieces. Well, maybe I should do an example. Suppose theta is pi upon 4. Then the unit vector will be the cosine of pi upon 4, comma, the sine. What are you doing? Who's crying now? Oh, she's crying because he won't give her the toy. Oh, shush. Yeah, you too. Shush. Actually, now I've thought about it, I probably should have chosen a better angle, but never mind. Are you happy with that would be the unit vector for this particular situation? Okay. So let's put the whole package together now and find a directional vector. So let's suppose we have a function f of 2 variables, x squared, take away y squared. So far, so good. And let's suppose we're interested in a directional derivative, oops, in the direction 1, 3. And we would like to get the directional derivative at the point 1, 4. So we have a point on the ground, 1, 4. That point goes up to the surface. We're then going to go in the direction 1, 3, and we're going to see what kind of slope the hill would be at that point, right above on the surface, going in the direction 1, 3. The notation for it is a little bit clunky. A capital D, a little u, so that's a directional derivative, unit vector, obviously, of the function f at the point 1, 4. If you want to do a general version of it, you would just do that, right? And the formula for calculating it is the gradient vector evaluated at 1, 4 dot product with the unit vector. Can you see why in Calc 3 we did dot products and unit vectors and all that good stuff? Can you see that we're actually now using it in another context? So now that I know everything I need to do, I'll have to do a bit of preparation here. Let's get the unit vector for this guy. So it's going to be 1 over the magnitude of v with the vector v. That one I can do in my head. I believe it's square root of 10. So we are looking at 1 over root 10, 3 over root 10. I know that's a bit quick, but are you comfortable with what I just did? Right. We need a unit vector, right? Now, I also have to find the gradient vector. Well, if you do a partial derivative with x and a partial derivative with y, which is what the gradient vector is, you get 2x, comma, negative 2y. And if you get the gradient vector at the point 1, comma 4, you are looking at 2 lots of 1 and 2 lots of 4. You get that guy. And you put the whole package together, then the directional derivative at the point 1, comma 4 is the gradient vector at 1, comma 4 dot product with the unit vector. And I've got the numbers here. I have a 2, comma negative 8 dot product with this guy. And remember how dot products work. X times X plus Y times Y. So it's going to be 2 times 1 over root 10, add negative 8 times 3 over root 10. So 2 over root 10, take away 24 over root 10. I believe that's negative 22 over root 10. And at this point, I would tidy it up. And there is our answer. The slope of the hill traveling in that direction at the point 1, comma 3, isn't it pointing downwards? Negative, right? By whatever numerical value that would be. Are we comfortable with the building blocks that you need to get a directional derivative, right? If they tell you V, you need to make sure it's converted into a unit vector, right? If they tell you F, you need to first get the gradient vector evaluated at whatever point they were interested in. And then the dot product of the two pieces, bingo. So far, so good?
Can you repeat what that answer is again? It's the slope of the hill traveling at what point from the origin?
Right, so can we pretend that that is the hill we're talking about? And this point here is directly below 1, comma 4. And we are traveling in the direction 1, comma 3. So let's say 1, comma 3 is traveling in that direction. So what we've just discovered is that the slope of the hill is pointing downwards, right? If you imagine this thing here, this is pointing downwards, and the slope of this rise over run thing is negative 11 root 10 over 5. What that tells me is if you were on the surface of that hill and you walked in the direction 1, comma 3, wouldn't you be walking down that hill right now? Right, you'd be traveling a downwards hill. The hill's sloping downwards. How steep is it? It's whatever that number is. Suppose the directional derivative is 0. I mean, 0 happens sometimes. What are you doing? If you're on, imagine the analogy, you're on the hill, right? At a certain point, and you're walking in a certain direction, right? Kind of northeasty, whatever you want to call it, right? You're walking in a certain direction, but there's no slope.
You're at the top or the bottom.
You could be at the top of the bottom, or couldn't you just be walking around like a belt, walking around it? So knowing that the directional derivative is 0, isn't that giving you a kind of clue to what's happening at that one instance in time? You know. Then we should do another one of these and then do an angle one, right? So I'm going to, again, we're only going to be dealing with 2-dimensional vectors, you know, 3-dimensional surfaces, but 2-dimensional vectors. Let's have a function, and it's going to be e to the power of xy. And we are interested in what this function is doing at the point 1, comma 2. And the direction that we're traveling is 3, comma negative 4. And so we are going to be finding the directional derivative of this function, right, at the point 3, comma negative 4. So that's what we're being asked to find. Let's find all the pieces. Yes,
0.12, because 3 negative 4 is the vector.
correct. And P is a 0.12.
For the directional derivative, you wrote the function we're solving.
Oh, God.
4, not 1, 2.
Did you all catch that? The deliberate mistake. I was just doing that to make sure you were paying attention. Well, you are nodding your head, I hope sarcastically. Good. That was just a mistake. Okay, I got you. Thank you for doing that. I would have screwed up if I hadn't noticed that. So the unit vector is going to be this fella. I chose nice numbers this time because that ends up being a 5th. And so our unit vector is 3/5, negative 4/5, which is kind of nice. Our gradient vector is going to be this guy. Oh, by the way, isn't this function symmetric? Not that it matters for this question, but isn't it? It's a nice symmetric function. So what am I going to get? Well, when you differentiate this with respect to x, you do get e to the xy. Do I get anything else? Partial derivative of this function here with respect to x.
You would have a y up front because
And
of
then,
chain rule.
agreed. And when you have an x for the other one, because of symmetry. And let's evaluate the gradient function at 0.1, 2. So this one would be 2e squared, and this one would be 1e squared. Are we comfortable with those two guys? Right. So the directional derivative at the point 1, 2 is going to be the gradient vector dot product with the unit vector. So it's going to be a 2e squared e squared dot product with a 3/5 negative 4/5. And what does that get me? It gets me 6/5 e squared plus essentially negative 4/5 e squared. And I believe that comes out as 2/5 e squared. So you're getting derivatives like dy by dz by dx and dz by dy. But if you used these two situations, wouldn't the direction be 1, 0 and 0, 1? And if you applied this to these formulas, do you know that you get the partial derivative dz by dx and the partial derivative dz by dy? Does that make sense? That these two are just special cases of this. So far, so good. Oh, by the way, this would be the unit vector direction. Let's do a angle version. Don't need the picture, but I'm doing it anyway because it helps my brain. Can you imagine that you're going to do a direction and it's going to be pi upon 3. And I'd like to know the directional derivative of this function right, this function at a point 0, 1. And the direction is pi upon 3. Now, we still need the same building blocks. The unit vector is going to be created using that. Remember, we did the unit vector of an angle. In this case, it's going to be the cosine of pi upon 3, comma, the sine of pi upon 3. Okay, which one of those two is the half and which one's the root 3 over 2? Exact value of cosine pi upon 3. Maybe I should ask the question that way. What's the exact value of the
1/2.
cosine? You're going to go 1/2. And what's the sine going to be then?
3/2.
How could we check? Whoops, not saying you're wrong, but how could we check?
Calculator.
Yeah.
Unit circle.
Oh, you could do a unit circle if you got one handy. I'm just going to make sure I'm in the right mode, which I'm not, so I'm glad I checked. Couldn't you just go cosine of pi divided by 2, and I've just wrong one. Cosine of pi divided by 3, that's fair. And bingo, it works. Now the gradient vector. Well, for this function, differentiate with respect to x and then with y. Well, what will you get? Well, you get a y minus a cosine x. And then you get, if you differentiate with respect to y, you just get an x. And then if you get the gradient function at the point 0, 1, you're going to get 1 take away the cosine of 0, 0, which is 0, 0. And the directional, oops, in the next page, I think. The directional derivative of this function at the point 0, 1 is the dot product of the gradient at 0, 1 with the unit vector. And this guy is 0, 0. And this guy is 1/2 √3 upon 2. And we have got a 0. So could it not mean that we're at the top of the mountain, right? The top of the hill. And if I try and walk in any particular direction, at least for a minute amount of time, wouldn't I be traveling with a slope of 0, right? It'd be in the flat. Or couldn't I be walking around like a belt on the surface at that given point? I didn't mean that to come out of 0, but I'm kind of happy it did. Because, you know, getting answers that come out to 0 are quite hard, aren't they? Can you imagine it'd be difficult to just get one, you know, off the top of your head. So that was a lucky coincidence that I got a 0 there.
So,
Yeah,
Professor
Yes.
Robertson, I have a question. So you keep talking about walking on the surface, but
Yes.
realistically, you could be walking through the object too, because this is like a 3D space problem, right?
Yes. Yeah. Well, I guess. Yeah. Well, you try not to walk too far, right? So if you imagine here, and I travel in kind of that direction, if I looked at it side on, I'd be traveling something like this, right? And then can you imagine what the tangent line might look at that point, traveling in that direction? But yeah, I guess if the curve, you know, these surfaces can be weird. If the surface curves in on itself, you would be actually walking into the shape. You're quite right. Now I think about it.
We do like a similar thing where if you have if you're trying to find a magnetic field at a point on a coil or a point away from a coil, the magnetic field comes out and it makes this like kind of donut shape. So here's your coil, and the magnetic field actually come out like this. And so when you have a wire or another, actually this should be aligned, another coil here like a transformer, you can solve for the induced electrical field or the induced electrical current at those points, which is very similar to what he's talking about, moving through the shape versus moving around it.
Okay, so I mean, you lot are just looking at this and saying, "Oh, I could see how I could use this idea in an electric motor, or I could see how this idea might work in a magnetic field or something." Yeah, there are lots of ways of thinking of what slopes are. Aren't slopes also a measure of rate of change? So what you're measuring, you could say what you're really measuring here is how is the height that I'm at changing if I walked in this direction? Is it going, am I going uphill, right? Is it a positive number? Am I going downhill? Now, I may end up walking into the shape because of the geometry of the surface, but it's still essentially, if I walked in this direction, how would my height change, right? How would the Z value change? And that's kind of what we're looking at. A very visual thing. I'm a very visual learner, so it's it's not scary to me because I know how my brain works. I can see things in my head of what that would look like, but don't ask me to draw it because my artistic skills are bad. Look at that. That looks like nothing. I mean, in my head, I can see really kind of clearly what I'm trying to express, but isn't it difficult the minute you try and do something that's 3D in your head and convert it into 2D paper and you're not a very good artist? So if my pictures are distracting to you, maybe you shouldn't pay too much attention to them. I'm trying to just visualize or try to write down in 2D what I'm visualizing in 3D. Okay. Any other questions? Oh, that was quite a good question to start with. So I'm going to look, or at least start by looking at some of the questions from our homework. So we get a look at, or see what they do. This one is a version of question 1. I'm just going to change it quite a lot. Here is our surface, a nice polynomial. Here is the coordinates of the point and the angle they want. I'm going to change it to 2/3 pi, okay? We are being asked to find the directional derivative at the point 1, 4. Would you agree that's a pretty standard looking question, right? I've covered, actually the one I just finished, isn't it very similar to that? So when you're finished, won't that be a number? It might be 0, it might be 42, it might be -1/2, but it's a number. Directional derivative is basically telling you either you can think of it as the slope of a line in a certain direction, right, how you're changing in height, or you can think of it as a rate of change in a particular direction, which can be helpful as well. So I need the unit vector, and that's going to be the cosine of 2/3 pi and the sine of 2/3 pi. Okay, any volunteers? What's the cosine of 2/3 pi? And you better be telling me a negative number, right?
A -1/2.
But isn't this one still positive?
Yeah.
Yeah, okay. I need a gradient vector. I don't think that is, I mean, hopefully it's becoming kind of mundane now. Yeah, I know how to do these, but we still need to do them. So I get a y cubed take away 2x when you differentiate this with respect to x. And I get a 3xy squared when you differentiate this with respect to y. And then I'll evaluate it at 1, 4. So it's going to be 4 cubed take away 2, and it's going to be 3 times 1 times 4 squared. Okay, 64 take away 2 is 62. 3 times 16 is 48. And there is our gradient guy. And to get this one, it's going to be the gradient vector times the unit. So it's going to be this ugly guy and a dot product with this guy. So what do I get? I get -31 when you multiply those, and I get plus 24√3. Now, if they want the exact value, isn't that the answer? I can't really do any style points in that. Would you agree? They're just separate. If they wanted the answer to 2 decimal places, wouldn't this be the point where we just go to your calculator and hit some buttons and round it off to whatever accuracy is required? Before I forget, will you say, well, it looks like most of you have done it, but just to remind you, put your last name down for attendance. And let's show you the next couple of questions from the homework. So the one I've just done was essentially that question 1. I think I'll do it a little bit bigger. Pretty straightforward. You agree? Here's the function. Here's the point P. Here's the angle. You're done. Right? A little bit uglier, but okay. If I was going to do this question, how would I rewrite this fella to make the differentiation, possible?
8x plus 9y to the half power.
Right, and be, do a chain rule. So remember the times 8 and the times 9, depending on which one you've got, right? I would probably do a little bit of style points on this one. So see when you do the derivative with respect to x, 4 on the top over the square root of 8x plus 9y. And the reason you're going to have 4 on the top and not 8 is because the half and the 8, merge to get you 4. The reason why I said 8, I would suggest you do that piece of style points is when you plug the numbers in, and do you notice that there's no indication here of accurate, 4 decimal places? Since they want the answer to be exact, won't it be much easier if you've got a number over a square root than a number to the power of negative a half, right? It's just not going to be pretty if you leave it like that. Here we have a function, the point, and that guy. That guy is called u. What does that tell you?
Is it the unit vector?
It's already a unit vector, so you don't need to find the unit vector. It is. If it's a unit vector, the convention is we tend to call it u. If it's just any old vector, it will be called v. So here's another unit vector. Now, we've moved on to 3D. But isn't it the grad of that is doable? Agreed? And isn't that already the unit vector? So we're good to go. Can't you plug them and boom, you're done? Could I do a direction vector in 16-dimensional space because I want to do string theory?
You could, but I'm not sure how you would visualize that.
You shouldn't even try because you'd hurt your head, but it's doable, right? So once you've got the concept of directional derivatives, it may and probably will, when you go higher dimensions, lose all meaning to your brain, right? Because we live in a 3D world, and I guess if we're really clever, which I'm not, you might be able to visualize what a 4D world looks like if you think of time as being the 4th dimension. But that's as good as our brain can cope with. Can you imagine directional derivatives in 16 dimensions don't make sense to us anymore because we are not really creatures that live in that world. Right, and you plug it together. I mean, they're really nice. Do you see they ask you for the gradient? They ask you for the value of the gradient, and then they go and ask you the answer. You would have to do those two guys anyway, wouldn't you, before you did this? So they're kind of just helping you. I'm getting feeling I'm doing deja vu here. Would you agree that they're just changing the numbers? They're not really changing the question. Right, a different function, different angle, different number, but apart from that, we're good to go. As this is going to be the last question I'm talking about, do you need to do something in this question that you didn't need to do in that question?
You'll need to find the unit vector.
Right. Do you know the biggest mistake I make in these, apart from the fact I can't count, is sometimes I forget to do the unit vector thing. In other words, I just use -10, 24. Now, if you do that, won't your answer be much bigger than it really will be in the real value? So hopefully you'll look at it and maybe notice that bit. That's what I would watch. Okay, I'm calling it good. Does